Give me just a second. Not sure why it does this now. It used to not do this step, but I have to wait for just a second. All right, there we go. And here we go. All right, looks like we're pretty good here. So I think we're only missing one. We'll worry about that later. Okay. And so I want to talk a little bit about your presentations, and maybe this will speed things up if I go through a very brief set of thoughts at the beginning. Then I'm just going to keep looping around one-on-one, just like always. So I'll do the breakout rooms in just a second. But that said, I want to show you a couple of things. Most of these files are all linked, and you know where they all are. But let me mention a couple things about these files here. All right. So our goal today is to practice making a good talk. The talk itself and what your topics you're talking about don't really matter. It's about going through the motions of making a talk. All right. So that if you have later stuff where something's important on it. Okay, great. So let me show you where the, oh, whoops. Whoa, that's not what I wanted. I want this and this in here. Let's just go back a few. All right. So in this case, here's robjorstad.com. You click Phys161 and you go to lab, and then there's all the links that you need. There's error analysis if you're into that. There's lab manual appendices. And if you scroll down here, there's these same things I think are linked in the Canvas site as well. So if you don't want to go looking around, but there's the sample presentation. I made a sample Excel spreadsheet and a rubric. And again, all this stuff should be linked in Canvas, so you don't have to go looking for it. Let's look at the sample presentation now. And I've been kind of messing with it a little bit, just showing people all day. So let's pretend this is the talk, whatever. Notice I made this in a hurry, so there's not a lot of images. In general, this is what you want to get in the habit of doing. Put a relevant image on every slide if possible. That may not always be possible, but generally speaking, when you're giving a talk, you want something pretty for people to look at, but you don't just want something random that you've just got off the internet or from clip art. Usually you want something that relates to your talk in some way. All right. So you could do a still photo or a screenshot of your motion or a device you used or something. And again, it's a little contrived for this one. It's going to feel a little bit cheesy on the theory because it's so light. That said, next up, if possible, while this is not always true, we usually want to go right to a question. We're giving a scientific talk. Ask the reader something. Now, I can help you come up with a question, and the specifics of your question don't really matter that much as long as you're asking something. A good trick is go down here to your conclusion slide and figure out what you can conclude and use that to make your question. You can literally cut and paste this slide after you make it, bring it back up to the front, paste it in, and then delete the answer, right? And that is a way you could actually make your question slide. So again, it's a bit contrived today. So some of you might be, can we model the motion of a bicycle as 3 stages of constant acceleration? Or is a ball in free fall when we throw it? And then what is the force that the hand exerts? Or what is the coefficient of restitution as a ball impacts the ground? So for those of you that had a ball bouncing, or can we accurately model the motion of a, so make up a question there and I'll help you with that. Is it going to be perfect today? Probably not, but I'll try to help you with that. Okay, procedure. Notice what I say here. Show a picture or a video instead of this bulleted list. Assume your video will fail, right? And then have a backup plan. Maybe that backup plan is to include some screenshots, or maybe you have a second copy of the video somewhere. But it's just videos notoriously fail on people, and then they're sitting there twiddling their thumbs because they were counting on it. All right. So theory. So one thing you could do, again, notice there's no images here. This looks pretty boring. People might have different equations here, but a lot of you probably have something similar to this. But again, spice it up with a picture of some kind, okay? All right. And then Maybe this is a different theory that applies to some other problem, whatever. Okay. So then we're ready to get into the data. Notice how boring these slides look. Boring is fine, right? You don't have to spend all day picking the right template and making it look pretty. A lot of times those templates can be distracting, especially when we get to data. Look at this plot. Notice these are 18-point font. Okay, notice the variables are in italics. The units are not. The grid lines are not so in your face. I probably could even make these a little bit weaker, like a little bit lighter gray or a thinner line. But there's a clear difference between the grid lines and the axis themselves. And the plot covers the whole frickin' page. Okay, not some tiny little plot. Next, I went in here and I actually made some little slopes. I did some slope calculations. How did I do that? Let me show you. Let's say this is the data. I literally went into Excel, and if I could show you right here, this is the command I used to get the slope between 0.1 and 0.2 seconds. I literally typed this in, and I'll show you this live over here. Whoops. I'll just type in equals. Whoops. I can't type the word slope right now. Equals slope, and notice it tells me first type the y values. So if I want the slope of an xt graph, the y values would be x, and the x values would be t. If I want the slope of a VT graph, then the y values would be v, and the x values would be t. So just watch out for that. But say let's say I wanted to get this slope right here. I could do this, comma. Now I hit the x values. In this case, that's the t's. This would get me the slope of a VT plot. Great. So now I literally just, there are other ways to do this, but the way I chose to do it was literally get these numbers using that slope command in Excel, and then you could do this. And you could argue, well, this line doesn't show up that well, whatever. But again, 18-point font or larger so people can actually see it. So that's a quick way you can get that. Now check this out. This is something that's not in there that I just added today. Here you show the graph. Then you say, here are the slopes. If you wanted to, you could animate these in one at a time, right? Let's say I don't want to be, right? This is too much information. I could go in here and delete this one, right? Just go in here and delete this. And then I'm going to copy this slide and paste it. Are there other ways to do this? Sure. Could you use the slides animations? You bet. But this also works pretty well. And one of the things that's nice about this is if you make, again, I don't know if you noticed this, you make this full, most complicated slide first. You make this slide first, then you make multiple copies of it and delete stuff so that when you walk through the presentation, you can say, here we go. And then you could say, look, between about 0.1 and 0.2 seconds, the velocity is this. Notice then at approximately 0.5 to 0.6, we get this value. And as we go even faster, we see it's approaching some value that's about 4.5 centimeters per second. You're controlling the flow of information to the readers. And so if you do that, this is a nice way to kind of keep them going where you want them to be. All right. Now check this out. This isn't in there. Look at this slide. Why did I do this? Notice the time axis on the upper plot and the lower plot match perfectly. Okay, I spent some time lining them up so that now I could say, well, look at this. Right here, at this point in time, the slope of the xt graph is supposed to be about 2, right? That means the velocity should be about 2. Looks pretty reasonable. Furthermore, right here, it's supposed to be just under 4. It looks like it's just under 4 right there. And finally, et cetera, et cetera. This leads you to a logical segue. Whoops. All right, then you're like, well, why don't we discuss the VT plot next? So you just keep going, right? Now let's just hit the down arrow. All right, well, let's look at the VT plot in greater detail. And you can start doing the same kind of stuff, right? Oh, great, or whatever. And then maybe you have some crazy function if you wanted to do that. This was a random thing. You could talk about these areas, right? And notice you could animate these in if you wanted to. And then maybe you could bring it back to the XT plot and say, well, look at this area. Notice this implies, whoops. You could say, look, The area here says it's supposed to be about, we're relating these things, and that gives you something to talk about. Okay. Now, another thing that you could do here, okay, and then we say, okay, let's wrap this up. And then, as you get close to the wrap up, you may want to have a slide in here that's kind of fun. For example, if you did a video of bicycling, you might throw in a random statistic about bicycling or something you read on the internet that's slightly entertaining, keeps the crowd lively, and then you could go wrap up with your conclusion. What did we find? Can we model bicycling as a 3-stage constant acceleration process? Great. Or running, you could talk about, running versus animals, or running versus humans, or running forwards versus running backwards, or all kinds of things. If you're doing a free fall experiment, or you're doing forces of hands, you could talk about, oh, what's the largest force that a hand could exert? Or what's the typical force? Or maybe you're that group that had balls bouncing off a surface. You could talk about the coefficient of restitution. If you were a group that did some oscillations, like a pendulum swinging back and forth or something bouncing, right? Maybe you might, I guess the oscillation is mainly what I'm thinking of. You might actually have a slightly busier theory, and I could help you with that. All right. So you might have different stuff in here, and then we're not having to hear the same boring talk 6 times in a row. One last piece here before I let it rip. Let's go over to here. And this is something you may not be familiar with. So I'm going to show you something that's kind of cool. That's an interesting thing. Like, let's say I have this data right here. For whatever reason, I have this data. XT, and you notice I'm kind of ignoring the AT data. You guys are going to have the AT data in your graphs, or sorry, in your talk, but you have probably noticed that your AT data looks terrible. This is totally reasonable because remember, the X values have errors in them. The velocities that you calculate are then have 2 errors that are used in that calculation. And then you use 2 velocities to calculate each acceleration. So you've got 4 errors adding up. It's very plausible that you get a lot of noise in that AT data. If anything, about all that's good for is if you can kind of look at it and say, well, it kind of looks positive or negative in the right areas. And that's about it. Okay, don't try to read too much into the AT plot. Focus on XT, VT, and their relationships, and slightly talk about VT, how it relates to AT, and see if that works. If it doesn't show up, that's fine. Still show it. You should all show the AT data, even if it looks terrible. All right, I expect it will look terrible. Every once in a while, it looks okay. All right, that said, let's say you are doing a free fall experiment, or it touches your hand and it's bouncing into something, and you want to figure out something about forces, right? If you wanted to figure out forces, any of you could do this. Or if like you're running and you want to figure out the average force that you're exerting on the ground in the horizontal direction while you accelerate, check this out, right? So maybe I'll go right to here. Give me just a second. Okay. Whoops, let's start down low. Okay, let's say, looks like I was doing an experiment where a ball is being thrown up in the air. Think about this. This is supposed to be a hand throwing the ball up. It flies through the air and it lands on another hand here, catching it. Well, for the part when it's in the air, remember, a thrown ball is in free fall, or a dropped ball, or whatever. So in that case, we'd expect the acceleration should equal g in the negative j hat, or a sub y is negative g. That's cool. But what about the part when it's touching the hand? Think about it. I'll do this while it's being thrown upwards right now. So imagine you're throwing this upwards. There's the weight of the ball, and then there's the force of the hand, and it's going to accelerate upwards. If you do a quick FBD, you can get the force of the hand is equal to mass g times the acceleration. But don't forget, you can get acceleration from the slope of a VT plot. Cool. All right. And for the free fall part, I'm going to show you this in just a second. Imagine you have a VT plot for just the free fall portion. So you look in the video and you figure out, okay, what time does the hand lose contact, or what time does the floor lose contact? You could do a free fall section. And you could do this function called line ST. This does line regression statistics, more in just a second. And that will calculate the slope. Well, if you calculate the slope, that gives you a value for G, right? This value here. And I should be careful. Slope should be negative G, shouldn't it? Because it's depending on how you rotated your coordinate system. Okay. But now we can also get an error in that slope. Now, a lot of people confuse percent uncertainty or percent error with percent difference. They're not the same thing. Percent difference is how close your value from your experiment is to 9.8, the accepted value. Percent precision or percent error or percent uncertainty relates to how crappy you think your equipment was and how that relates to that quality of measurement. So one thing we could do here is we could get the error in the slope, and that is a statistical estimate in the error in your value of G. And so you could get a percent difference and a percent precision separately. If the percent difference is much larger than the percent precision, that's a bad sign. It means your equipment was pretty good, but your result was way off. That's a bad sign. On the other hand, if your percent difference is about the same size or smaller, that says, look, I was 3% off. My equipment's good to like the 3 to 5% level. I would expect to be 3 to 5% off. That's a good result. It's in good agreement. So those are things you can do. Now, how do you get this error? Let me show you here. Let me go back to screen share. It turns out we could do, this is not the be all end all. This is one estimate. Okay. But this is a cool trick. We could type equals line ST. Okay. And I've got this in the appendices with screenshots and everything. So I'll give you that in just a minute. But first, let me just show you how this works out. Notice it tells me it's a lot like the slope. First, I highlight the Y values. So let's say I want to get these Y values. Let's say I just want to do the first two that much time, right? Now I hit comma. Now I hit the X values. Again, the X values in this case are actually time. I'm getting this, it's related to the slope of the VT plot. Now here, this is just true, comma, true. That just basically tells it to output the information in the way we want. Okay, that gives me the slope of that. Now if I do this, fill it right and fill it down, and then if I think I hit F2, Control Shift Enter. Now a lot of you have a newer version of Excel and it'll do this automatically. What this does is the following. This number right here is the error in the slope. The top number is the slope. The number right below it is the error in the slope. So what that means is for this particular set of values, I said that A is equal to 9.6 plus or minus this number. Ooh, this is kind of a weird one, right? It's 0.10. Normally, ooh, so this is a little bit, okay, so this is a good example to go through because it turns out the sig figs on this are slightly tricky. All right, let me redo that. And I need to clear one other thing. Let me show more of these sig figs again. All right, so here's the deal. The error in the slope should have 1 sig fig. It's an error calculation. However, if I round that to 1 sig fig, it looks like the first digit is a 1, so we would actually keep 2 digits. So in this case, we would say in this value, A is equal to the slope, 9.6, and then this is the uncertainty in that slope, plus or minus 1.0 meters per second squared. And if you wanted to get this as a percentage, you could actually do 1.0 divided by 9.6, and that's going to be just estimated, right? Isn't that basically 1 out of 10? So this is about 10%. So we see I got a value of acceleration of 9.6 plus or minus 1 meter per second squared, or 9.6 plus or minus 10%. And that gives you an error calculation you can explain. Now think about this. If you're doing the bicycle or the running demos, this relates to your work as well. What you could do is you could say, what is the acceleration during the acceleration stage? And you could say, okay, I got the slope. I could get the error in the slope, and I could say, well, the acceleration is constant to 10% or 20% or 5%. And so it helps you quantify how constant the acceleration is. What do these numbers mean? It means about 68% of the time, most of the values fell within about 1 of 9.6. So most of the values are within 1 of 9.6. All right, now that was a lot. I promised I would show you where that is. If you go up here to the Lab Manual Appendices, you can hit Lab Manual Appendices. And let's just hit Control F. And you just type line ST. And so there it is. And it's got all this information for you, including screenshots, and it gives you the information, what all this crap means right there. Tells you everything you need. So the reason I'm telling you this is it can make your talk sound a little bit nicer. If you say, here's the thing we measured, and this is how well we think we measured it. That's all that's about. I'm going to stop the